Today, I wanted to talk a little bit about how we can build bigger programs than the ones that we've been sort of demonstrating with my silly pen and paper computer, with my little robot and his array of pigeonholes that represent the CPU and the array of memory where all of the data and instructions, that is the recipe for the robot to follow, are stored. So let's sort of refresh our memory a little bit. And I'm going to draw my little robot over here. And I've probably picked the one pen that is going to run out in the middle of this. But I have a box of them now because of this. And so our robot lives over here. And he's got his abacus. And then over is a huge array of pigeonholes, which are like, I suppose, letterboxes in an apartment building would be another analogy that's more appropriate.
Lockers, yeah, that's a good...
Lockers, there you go, that's a good one as well. So, and in each one of those is numbered, so 0, 1, 2, 3, 4, 5, up to like billions of them, as we've discussed before. And the robot also has a little bit of a temporary working space, which we call registers. They are like a small amount of local storage, little post-it notes that he's got, that we maybe call the A register or the B register, and he can read numbers in and out of them, and he can add them together, and then he can put the numbers back inside this big pigeonhole array. Fantastic. That's where we were before. And we wrote a Fibonacci sequence program, if you recall. Now we're into a bit that we are going to do over and over and over again. Step 5, and we showed as well that the various types of instruction, like read the next number and put it into the A register, they can be encoded as numbers, and those numbers themselves can go in the pigeonholes. And so there's this sort of beautiful combined storage for both the data and the program itself, all in one place. So wonderful. But it was kind of tricky to do anything, tricky to see how you could do anything like meaningful other than simple toy programs. And that's because when we're writing code, we don't just write loads of instructions one after another. In fact, we don't typically write instructions anymore, but that's a whole other topic. We sort of break the problem down into smaller pieces and then reuse those pieces over and over again and usually we give them a useful name. I'd like to show how the computer gives us the tools that lets us write little snippets of code that can be reused. What I'd like to do first of all is write a snippet of code that I'd like to reuse. So I'm writing a little game, and this is obviously a hypothetical thing. I'm writing a little game, and one of the things I want to be able to do is find the magnitude of some vector. It doesn't really matter what this is, but the magnitude of a vector is how fast something is moving in what direction. So for example, you might want to know how quickly you're going to hit a wall if you're a player or something like that. Or it's also the distance between 2 points if you use the magnitude of the vector between them. So you could say, am I about to crash into something? Those are the kind of things that you might want to do. And the magnitude of a point, and this is a 2D game because this is simple, is the square root of x squared plus y squared. Again, it really doesn't matter. It's just a little piece of code that we're going to use all over the place, and we don't want to have to keep writing out over and over again. And so in my sort of funny pigeon made up assembly language, that's going to look something like this. The first thing we need to do is we need to work out what x squared is. So I'm going to say mul for multiply. And in this particular sort of syntax, I'm going to say there are 3 operands, 3 things that are going to appear on the right hand side of this. The leftmost is like where the result is going to go. So I'm going to say t0 to say just some temporary place, and we'll talk about what these t's and whatever are in a second, comma x, comma x. So what this is saying is multiply x by x and put the result in t0, which is just temporary storage. One of the other registers that we're going to say the robot has access to here. And also we're going to assume the robot has an x register and, as you might be able to guess for the next thing, a y register. So effectively this first instruction does x squared, second instruction does y squared. We're going to add them together into sort of t2. So this gives me x squared plus y squared. And then I'm going to say I want the square root, which I'm assuming this computer can do, which is actually very uncommon for the kind of computers that I'm drawing here. But, I'm allowed to make up whatever I like, it seems. And I'm going to say wherever the result needs to go, I'm going to call something called result with the square root of t2. Okay, so those 4 instructions are how we would get the magnitude of something that is in x and y. Reasonable. And, again, we would put this somewhere in the pigeonhole array. So let's say it lives at address 1000, and let's assume that each of these instructions takes up exactly one of the slots we can see that this is 4 instructions. We could put it somewhere in memory. And then what we really would like to be able to do is somewhere else in the program say, hey, I've got something in the X and Y, and I'd like to know the magnitude. Can I just use this bit of code, please? And there's a way that the CPU allows us to do that with an instruction called call, C-A-L-L. So somewhere else in the program, so let's say instruction 10 in memory, we're going to do something like, move X with 10, instruction 11, move Y with 20, and then I'd like to get the magnitude of this vector, this 10, 20, and so I'm going to say call 1000, and that says I'd like to go and run the little program that's over in address 1000, and then we need a way to come back to here so that step 13, which is obviously the rest of the program, can carry on. So we need to sort of remember where we were and come back to it. And also we need a way over here in our little subroutine, which is the name for one of these snippets of code, or a function, sometimes you'll hear it being called. We need a way for this to say, I'm finished, go back to whatever you were doing before. So sort of the opposite of a call is, I'm going to put this in over here in 1004, is return or ret. Now we've got a way where we can write a little bit of code and keep reusing this same 1000 function, because maybe then we would say, like print out, I'm not just making up code here, print out whatever result is, and then we do 14, and we can do like mov x with some other number, move mov y with some other number, call it again, and just keep doing it. That's great, it's useful. And moreover, I don't have to think about this anymore. Somebody wrote the magnitude subroutine or function for me, and as long as I remember it's at address 1000 in memory, I can keep calling it until the cows come home, and everything's fantastic. So far, so awesome. But what if, for example, this routine over here in 1000 wanted to call another routine? Because, maybe the magnitude needs to go and do some other. Maybe the square root, in fact, isn't an instruction. We actually have to call the square root routine. Somebody carefully works out how to do a binary square root, which is a fun thing to do if you ever want to try it on pen and paper. And, you write a program to do that. So now this 1003 becomes a call. And now we've got kind of a routine that calls a routine that calls another routine. And so how is the computer keeping track of where the heck it was before? I mean, like, I go up the stairs sometimes and I can't remember what it is I was meant to be doing when I come back down again. So how does the computer do this? We need to introduce a new register. And I'm going to have a new box over here, and it's going to be called SP for stack pointer. And we're going to use a stack. I know Computerphile would have covered stacks before. And when we think of things like stacks, we think of them as like a data structure. And typically data structures are things that we write programs to do. But this is going to be something which is going to be implemented by the CPU itself, in silicon, in the hardware of the CPU. So it has to be super, super simple. And luckily, the stack is incredibly simple. So what is a stack? Let's just do a quick recap. A stack is a nice pack of, if I can get them out here, Post-it notes, where I would like to be able to keep record of what I've been doing before, or whatever's happened before. And then I want to be able to put things on the top of the stack, and we call that pushing. And then when I'm done with them, I want to pop them off of the stack. Push and pull would make more sense, but actually we say push and pop. Pop them off of the stack in the reverse order that I put them on there. That's the key aspect here. So, for example, if we were over here, let's assume I'm going to write over here 2000 is going to be my square root routine. Oops. And it's going to be lots of clever instructions that I don't know how to write off the top of my head that actually calculate the square root of whatever is in T2, as it happens. And we'll come back to that in a sec. And so this instruction at line 1003 wouldn't be a square root. It would be something like call 2000. So we just ignore the square root for now. What we're going to see here is, let's assume our robot is here at instruction 10. He executes instruction at memory address 10, the move, 11, 12, call. He's now going to go to 1000, but before he does that, he's going to write down 13 to say, this is where I need to come back to. And he's going to push that onto the stack. So we're going to, for now, the stack is going to live over here in this corner. And now he carries on over in instruction 1000. He multiplies, he adds. Now he needs to call to 2000, but when he's finished with 2000, he needs to come back to 1004. So I'm going to write 1004 on my stack and put it on the top. Now notice that's hiding the 13, and now we've got the 1004. He's going to go and do the square root routine, which I haven't written out. He'll hit the return at the end of the square root routine, and the return says, go get the most recent 1004 and then go there, and then throw this away. So we're going to take the 1004 away, and we're going to throw it away. So now we come back to 1004. Oh, and now we're going to return again. As it happens, there's no extra work in this particular case, but there usually is a little bit more work. And now we're going to return. We're going to get 13 off this piece of paper. And that means we're going to go back to address 13 and we carry on with our print and result. So that's fantastic. We've got a way of keeping a sort of arbitrary number of the things that we were doing before to go back to. Fab. But how do we implement this in hardware? So I'm going to get my little stack pointer and I'm going to use this terrible little piece of post-it note. And what the stack pointer really is it points to where the stack is in memory. And just like everything, we can solve our problems by finding a way to store them in this massive array of pigeonholes. So we're going to say that the stack pointer initially starts over here somewhere in memory. And so effectively this stack pointer will have, let's say this is address 5,000. This is address 5,000 over here somehow. So our stack pointer is 5,000. When we push, what we're going to do is we're going to write the value into the location that the stack pointer is currently referencing. So we're going to put our value, in the case of this, it would have been 13. Then we're going to walk the stack pointer backwards, and we'll talk about why it goes backwards in a second. The next call would have put, 1004 in here, and it would have moved the stack pointer forward. And then obviously popping is the reverse. We move the stack pointer up one, we read the number that's out of there, and that's where we go, and then we move the stack pointer up again. So that's the mechanism. It's super simple, and you'll notice that I put the stack pointer somewhere very, very high up in memory, because typically we start our programs and data and everything starts at the bottom of our giant array of pigeonholes, and then we put the stack pointer way off in the back, and we hope that they never cross over each other, because if they do, we've got big problems. And I mean, there's a name for that. You're probably thinking it right now.
There's a website called it, isn't there? I think, isn't it?
There is a website that's called it for exactly this reason. It's like a known programmer problem, and it's the website is a sort of solve my programming problem site, and it's called a Stack Overflow. And so the stack itself is an area of memory that we have reserved for this purposes of keeping a sort of temporary track of where we were before, and the hope is that we make that area of memory big enough that you don't write off of the end of it. Now, obviously, modern operating systems and everything have all sorts of clever protections to prevent that from being too much of a problem, but there are still problems associated with this. That is the mechanisms by which we call. But I would like to demonstrate this a little bit better by writing our Fibonacci program again, except in a different way. So I'm going to move these out the way. And if you remember our Fibonacci program, it calculated by essentially starting at the beginning and just walking up all of the Fibonacci numbers and keeping track of what it had done before and just adding things together. There's a cute way of defining the Fibonacci sequence, like for the nth Fibonacci sequence, in terms of the previous Fibonacci numbers. And you can actually write a program to compute it that way. It's terribly inefficient and you shouldn't do it, but it certainly demonstrates some of the things that I'd like to talk about. So let me just write out the mathematical definition, and I'm no mathematician, I'm barely a programmer. The function Fibonacci has the value, of n, some number n, and now we're turning into, I feel like we're turning into the sister channel right now, but it is defined to be n if n is less than or equal to 1. That gives us, if n is 0, Fibonacci is 0. If n is 1, Fibonacci of 1 is 1. But other than that, Fibonacci of n is Fibonacci of n minus 1 plus Fibonacci of n minus 2. So that's the other case. So if n is less than or equal to 1, we just know the answer. Otherwise, we can define it in terms of ourselves, which is a cute way of doing it. Let's quickly try writing that program right now. So I'm not going to write the addresses on the left-hand side. It doesn't really matter that much. I'm just going to give a name to fib. And this is typically what we do if we're writing assembly code, is that we give names to things, and then we let a computer program work out where all the addresses are actually going to be. And in fact, the computer program also works out all of the numbers and things like that. We don't have to do most of that work for us, which is fun. So like the first thing we're going to do is, well, let's take care of the initial condition. So I'm going to say compare n r. But n is what? I mean, how many registers has my computer got here? I mean, I could make up another one called n, but I'm going to run out of them very, very quickly. So we're going to pause here, and I'm going to have to come up with a better way of doing this, because eventually I'm going to call Fibonacci again, and I've already used n, and so how many n's can I possibly have? So what we need to do is come up with a convention about how we're going to interact with other sub-programs. And that convention is essentially a contract between the caller saying, hey, I expect this environment, like these registers should be allocated in this way, and the callee that says, okay, if I need to use one of the parameters, or if I need to use some registers, I know which ones I'm allowed to use, which ones I'm not allowed to use, and that kind of thing. So it's a bit like, when you have a contract with a person, and you say like, okay, you're doing some work on my desk temporarily. Feel free to use the desk, but can you put it back exactly how you find it? Now, that would be a very strict contract, but that's not totally unreasonable, I think. But, maybe you say, I don't really mind what's on top of the desk. I can just chuck that in the bin. But don't muck around with my book collection, please. That's fine. Or if you do, just make sure the book collection's back again. That way I can rely on you haven't fiddled around with like my alphabetized sequence of books. And so what I'm going to do is I'm going to make up a calling convention for my made-up program, my made-up CPU here. And instead of calling the registers A and B and whatever, I'm going to call them R0, R1, and I'm going to have, say, 15 of them. There's 15 registers, sorry, 16, off by one errors. 16 registers, R0 through R15, and that's all the robot has access to, but obviously it has this big memory. So what I'm going to say is, if you are calling a function, if I want to pass in an argument into that function, if I want to give it a value to work on, I'm going to put the first argument in register 0, the second one in register 1, register 2, and then register 3 for the others. So this particular operating system or program, whatever we're going to call it, this calling convention only allows passing up to 4 arguments for the simplicity. Now, if I call someone else's function, maybe I'm doing some temporary work myself and I'm using some of the other registers to store values, and it would be a pain if I had to store them every single time somewhere. I don't know where we would store them, but like preserve them so that when I call a function, it can use all the registers in the whole computer, and then when it returns back to me, I have to somehow recover from this, right? That would be annoying. So I'm going to say that you're not allowed, if you're a function, you're not allowed to change the contents of R4 through R15. So the rest of the registers you have to leave alone. Now, that doesn't mean in principle you can't change them. You just have to make sure you put them back. So again, for our desk analogy, you can move those books around all you like, just so long as when you let me come back in, you've put them back the way you found them. Which, as a parent, I'm sure you're like, please just leave it how it was before. Right. So R4 through R15, we're going to say you have to preserve them. And then the last sort of part of this, so these are the parameters coming in. And then this is the sort of do not touch, do not touch, do not. And then last of all, if your function returns a value, as our Fibonacci sequence will, let's just say the result goes in R0. That's a convenient place for the result to go. So now we've got a little contract, and this is going to help us write our Fibonacci routine in a sensible way, but also it means we can interoperate with every other program without us all having to decide on, magnitude uses T0, but square root uses resultant T2. That would be too confusing. If we just rephrase this in terms of the correct registers, maybe we have to do a tiny bit more work and we have to be a bit careful about which registers we use, but it means we can interoperate with 2 different programmers' code. And that's important, right? And usually the second programmer is you yesterday, and you're trying to work with the code that you wrote before. So, right, now we're going to apply our calling convention to our Fibonacci routine as we go. So the first thing we know is that the n value will be in register 0 because that's the parameter to our function. So I'm going to compare R0 with 1, and then I'm going to say branch if less than or equal. I'm picking these words because they are very close to a real CPU's architecture. Branch if less than or equal to end. And that's just going to say, we're done. And look, as it turns out, R0 has the result in it because we return n if n is less than or equal to 0. And I'm going to write end all the way down here. And end is going to be ret. So I'm effectively saying, jump to the end and finish. And then you'll go back to the caller. Fabulous. Okay, so the next thing we need to do is we need to get Fibonacci of n minus 1. So what I could do down here, and I'm going to leave some space here because I'm going to have to do a little bit more, and I haven't left enough room now I look at my... Again, I'm going to rely on Sean's editing to make this look okay. Is we're going to say subtract R0, R0, and I'm going to use a hash 1 to mean this is not a register, this is the actual value 1, which is something that, again, my architecture is going to allow me to do. And that is, I'm going to say, let R0 be R0 minus 1. That is n minus 1. So we're saying that n, the input to the next routine, is n minus 1. Fantastic. And then I'm going to call fib. Wonderful. So now, having done that, we've got the fib of R0 here. So we now know what... so this gets fib of n minus 1. Wonderful. And now we want to get fib of n minus 2. But unfortunately, we've just lost whatever n was, right? We've got the result of n, a fib of n in R0, but we no longer have the original n value. Darn it. So I need a way of preserving it. So why don't I borrow one of the other registers that I know that fib, even though it's myself, right, it won't touch, or is not allowed to touch. So right at the beginning here, I'm going to say, let's put a copy of the input value into R4, right? We'll worry about... I've just realized I haven't left enough space again. We'll worry about the fact that we're mucking around with R4 in a second. So we've called fib of n minus 1. And then what I want to be able to do is say, okay, I want to now call sub R0, R4, hash 2, and call fib. So here we're saying R0, which again would be the input value to our fib, is equal to the original n minus 2. Call fib. Wonderful. Except that we've now lost the result that we got from the previous fib, which was in R0. Darn. So why don't we temporarily move it into R5? So what we've got here at this point is R5 is equal to fib of n minus 1. Down here, we now know that R0 is equal to fib of n minus 2. And we can actually just add R0 to R5. So now we're saying fib of n minus 2 plus the thing we remembered before of fib of n minus 1. And so there's a little bit more work that we've had to do here, but we've brought back the interoperability with any function, and we don't have to kind of come up with a different convention for everything. But we've given ourselves a problem. And that problem is that we've just corrupted R4 and R5, even though we said we are not allowed to touch them. So we need a way of preserving them and restoring them. Now, can you think of a data structure that we've just talked about that could preserve and restore values in a way that lets us kind of nest and keep going?
Does it involve Post-it notes?
It does involve Post-it notes. Exactly right. So, not real ones, although maybe the robot does use Post-it notes. I don't know. Okay. No, he has to use pigeonholes. He has to use pigeonholes in this here. So yes, we use
Post-it notes in pigeonholes.
Post-it notes in pigeonholes. I guess it is, yeah. What I really should have done, and I mean, I don't know if you can fix this in the edit somewhere, is that mov should have been here, R4, R0, and then directly before, once we've decided that we aren't immediately going to operate, we need to push, and the CPU allows us to do this as well. It lets us put arbitrary values on the stack. So here we want to say, I need to push R4, and then I need to push R5, which says, hey, preserve on the stack R4 and R5, do all of this work, because now I can use R4 and 5 as much as I like, provided before I get back, I pop, and then very importantly, in the opposite order I push them on because of the way that the stack works, pop R5 and then pop R4. And that is before the ret. So the original version doesn't use the stack at all. If R0 is 1 or 0, it just bumps straight to the end and we're done. But as soon as we know we have to call ourselves, we immediately preserve R4 and R5, do our work with some careful manipulation of R4 and R5 and R0 to make sure that we've got everything lined up right for our calling ourselves, and then restore order before we come back to return. And so that lets us write this recursive function, and we don't have to worry about running out of register numbers. We do have to worry about running out of stack, but the stack is in the memory of the computer, and there's a lot more of that than there are registers. So that helps us a lot. Although, if you're not paying, if you're not paying attention as a programmer perfectly to exactly balancing the number of pushes to the number of pops, if there was some mistake in here, for example, if this branch if less than equal jumped and actually got to the pops instead of to the ret, or we did the comparison after we've done the pushes and we go straight to the ret, then now our stack, which is mixing two things, it's mixing the where to go back to addresses with the numbers that we've decided to preserve ourselves. And if you get that wrong, or if you can trick a program into doing that when it's not supposed to, you can now take control of where the program is executing. Because if, for example, you can put the number 27 into R4 or whatever, and then contrive for that to be left on the stack, when it gets to the ret, it goes to 24 instead of wherever it was meant to go. And that is, rather unfortunately, a security problem if any of these numbers came from the outside world. But it is also a programming bug. But this is why we talk about stack overflows as being an issue. It's why we talk about issues with the program where you can take control of the stack and then force the execution to go elsewhere.
Is there one stack in a computer? Is it one stack for a CPU? Is it where is the stack? Is this in a cache or?
That's a really interesting question. So yes, it is. So this is a funny thing. So this is like where the boundary between the physical CPU and its registers, of which it has exactly one stack pointer. So that CPU has one stack pointer. The calling convention, which explains where things are going to go and whatever, is more of a convention that is not tied to the CPU. So, different operating systems even might choose to do things differently. And then the operating system as well, if you've got many programs running on a computer, or if you have many threads running, each thread will have its own stack. And the operating system does some magic to switch the stack pointer from one stack area to another stack as it switches between which programs are executing. And those kinds of subtle distinctions, which while they're not specific to the CPU, the CPU provides the primitives that you can build these things with. Those things that are sort of vaguely operating system again specific mean that, like, this is why you can't take code naively from, like, say, Linux and run it on Windows, because they might disagree on which registers have which values when, right? Even in simple pieces of code. So, but yeah, and typically, to answer your question about cache, typically because the stack is so frequently accessed, so we're forever pushing and popping things from the stack, it is almost certainly in the most warm cache, the level 1 cache of your system, and so it's relatively cheap to push and pop things to the stack. Whereas if every program, one solution to this, if we weren't recursive, would be if every program, every procedure had its own temporary little storage area where it stored the, like, R4 and R5 that it's about to splat, it just stores it there, then, first of all, you couldn't use recursion because you couldn't call yourself and all that kind of stuff because you've only got one place to put them. But secondly, it means every time you call a function, it's using its own area of memory, which probably isn't in the cache unless you've just done it. And so the stack kind of brings these great properties of relatively performant memory access times. And, also CPUs are really smart, and they're very clever at noticing that when you're pushing and popping to the stack, and they can often take shortcuts to avoid doing too many memory accesses, or at least making those hide away from the program in terms of the latency that they might bring. So it's a fun trick. And as having a hardware resource. I mean, actually, so just to be sort of amusing, some computers don't directly have a stack pointer, or they don't need a stack pointer. You could just pick one register and say, this is what I'm going to use this register to point at. It could be like R15. Let's just pick R15 is I'm arbitrarily choosing to use that as a stack pointer. And then maybe instead of having the computer automatically push and pop the return address, we could just have another register, which is like, where did I last come from? And we could call that, say, a link register. That's like where I came from. It's just one of them.
Bit like a program counter, that sort of a thing.
It's like a program counter. It just keeps the last one. And then if you want to return, what you do is you say, can you put the link register back into the program counter? And that returns. And now if you call another function, though, you now need to push the link register. And now you've built the stack. But that means you can choose whichever register you like as that. You can choose whichever way of doing it you like. I actually have a surprise. I'm going to, let's see if this works. And I'm sorry if this breaks and everything. I'm going to click this button here.
So what are we looking at here then?
This is a website called Compiler Explorer, which I'm involved in running. disclaimers abound
I think
here,
some people have definitely in the comments before spotted that you're involved.
They have noticed that I'm,
and it allows you to pull things apart, basically, does it? Or what's
it lets you write in various different programming languages on the left hand side, feed them into compilers, and then see what the results look like in terms of the actual assembly code that the computer is going to run on the right hand side. And I took a moment to write in C the Fibonacci program, and I've compiled it for the ARM architecture, which is what this is sort of vaguely heading towards. On the left-hand side is the code, and then the colors of the backgrounds represent which part of the C code, which is a higher level language, maps to which kinds of assembly instructions on the right-hand side. And while it's not exactly what I've written down on this piece of paper here, it is surprisingly close. Like we see that it unconditionally pushes a bunch of stuff. It does that comparison and goes to like end down here where it pops, and then this BX is to move the program counter into the LR, the link register. And then down here, we can see it's doing exactly what, well, I say exactly, very similar things to what I was doing by subtracting 1 and 2, calling Fibonacci and adding them all together. So the math checks out. It does. I have actually written something vaguely correct here. But yeah, so typically one as a programmer doesn't write stuff either on paper or in assembly instructions. We use higher level languages to do that. But they have to do the same thing. Ultimately, they all boils down to the same instructions, the same ones and zeros at the end. And you can tinker with it. So if I go over here and, maybe we're going to make up a new Fibonacci number sequence, which is actually fib of x minus 3 even as well, and make that less equals to 2, then in a moment or two, the whole thing starts immediately sort of recompiles and shows you it. And it works for tiny snippets of code, and there's 100 different things you can do with it. Yeah, it's fun, but obviously this is higher level than we've been talking about. Certainly, the left-hand side here is much higher level than the code I've been writing out by hand. But there's a reason why I wrote a website called Compiler Explorer that explores all this type of stuff. I'm really fascinated by it, and I find it really interesting, and I hope the viewers do too.
A sum of a bunch of square roots. And the other path is also going to be the sum of a bunch of square roots. And so the question we have is, how hard is it, given a list of square roots and another list of square roots, to determine which of them has a bigger sum? And it sounds like you think it's not going to be that hard.